Hello everyone and welcome to CSEN 601 Computer System Architecture. My name is Walid Al-Hifni and today I'm going to solve practice assignment 10. However, I'm going to explain how the control signals are stored in the pipeline registers. Then I will introduce the concept of the MIPS forwarding unit, which will be needed to solve the practice assignment. So let's start with the addition of the control unit in the MIPS pipeline data path. As you remember from the previous tutorial, we had 4 pipeline registers that were introduced in the MIPS pipeline data path. Each pipeline register stores some values that will be used by the next stage. Okay, so we have 5 stages and 4 pipeline registers. Each pipeline register is separating 2 stages. So as you can see in the instruction fetch stage, after I finish fetching an instruction and performing all the operations done in the instruction fetch stage, I'm going to store these results in the if/id pipeline register. So in the upcoming or the following clock cycle in the decode stage, I'm going to read this data from the if/id pipeline register and operate on. And after operating on this data, I'm going to store the result or the output of the decode stage to the id/ex pipeline register as if it is going to pass this information to the next stage. So we need some sort of a temporary storage between the clock cycles since each stage operates in a different clock cycle. Okay, for an instruction to finish execution, it needs to pass by 5 clock cycles, and in each clock cycle it will perform or operate on a stage. So in the execute stage, it's going to retrieve the data from the id/ex pipeline register, operate on it, and then store the result in the ex/mem pipeline register. So in the next clock cycle, the memory access stage will read the data from the ex/mem pipeline register, will operate on this data, and then will store the result in the mem/writeback register or pipeline register. Finally, the writeback stage will read the data from the mem/writeback register, will operate on, and thus we finished the execution of one instruction in the pipeline architecture. So as you can see, the pipeline registers act as buffers or temporary storage to pass the data from one stage to another, since we are not operating in the pipeline architecture on an instruction in one clock cycle. Remember, in the single cycle implementation, an instruction passed by all 5 stages in the same clock cycle, in one clock cycle. But in the pipeline architecture, an instruction will pass by each stage in a clock cycle, in one clock cycle. So it needs a total of 5 clock cycles to cover all 5 stages. So since at a given clock cycle we can have up to 5 instructions running in parallel and each instruction will be in a different stage, so we need to keep track of the values and the operands and the control signals of each instruction in our data path. So we have the pipeline register or the pipeline registers to store this data, and it can pass this data from one stage to another, which is from one clock cycle to another. Okay? In the previous tutorial, we never tackled the control signals and where do we store the control signals in the pipeline registers. As you remember, we have the control unit in the decode stage, and during the fetch and decode stages, we do not know any information about the instruction, which type, for example, R, I, or J, because the actual control signals are generated in the decode stage. So starting from the execute stage, which is the 3rd stage, I know the information about the instruction, its type, and etc. So actually, the control unit is present in the decode stage. As you remember, it takes as an input the opcode, and it will generate all the control signals accordingly. And thus, starting from the execute stage, we can know the control signals and which type of instruction we are executing, since the control signals are going to prevent irrelevant data from continuing in the data path and will only pass the relevant data needed by this instruction to continue further in the data path. So as you know, in the instruction decode stage, we try to map an instruction we fetched from the instruction fetch stage to all possible formats, to R, I, and J formats. So I'm going to divide this instruction to all possible combinations, because at this stage I do not know which type of instruction is this. I will know starting from clock or from stage 3, which is the execute stage, because in the decode stage the control unit will take the opcode and will generate the control signals, and then the control signals will prevent unwanted data from continuing in the data path. For example, if I'm an R-type instruction, I do not need bits from 0 to 15 which are entering to the sign extend module. Therefore, the control signals will prevent these values from passing in case I am an R-type instruction. Okay, so in the decode stage, I do not know what type of instruction I am trying to decode. Therefore, I am trying to create all different combinations or map it to all possible combinations. So, as you can see here, the control unit in the decode stage will generate all the control signals. All the control signals will be stored in the ID/EX pipeline register. So take care, because you are going to perform this in your project. All control signals of a certain instruction will be present in what? In the ID/EX pipeline register. Okay, so during the execute stage, I'm going to retrieve the control signals I need in this stage. Here, for example, I need the ALU control signal, which tells me what is the second input to the ALU. I am going to take the value of RT, or I'm going to take the value from the sign extend module. As you can see, the ALU source is the selection line to this multiplexer. Either I'm going to select the value of RT, which is read data 2, or I'm going to select the value of the sign extend module. Also, we have the ALU operation, or the ALU op control signal, which is a 2-bit control signal telling the ALU control which type of instruction is this instruction. So if it is a load or a store instruction, or it's a branch on equal instruction, if you remember from the previous tutorial, they have unique values. But if you are an R-type instruction, the 2 bits for all R-type instructions are the same. Therefore, the ALU control will need the help of the function bits to determine which ALU operation or which arithmetic operation should be performed in the ALU. So as you remember, the ALU control informs the ALU about the arithmetic operation to perform. Thus, we need the ALU op control signal. If I'm a load or a store or a branch unequal, or any I instruction type or J instruction type, I am good, because I know exactly what instruction I have. But if I was an R-type instruction, the opcode is always 6 zeros, so all R-type instructions share the same opcode. So actually, the control unit cannot alone determine using the opcode which instruction you are performing. Are you performing an addition or a subtraction, for example? Therefore, we need the help of the function bits to enter to the ALU control to inform the ALU about the operation to be performed, whether I'm a subtraction instruction, so I need to perform subtraction, or I'm an addition instruction, so I need to perform addition. Okay? Also, you'll find something new, which is the regdest control signal. This regdest control signal was used in the write back stage to select the destination register, whether I'm going to write my value to register RT or to register RD. Okay, so it selected the destination register. This logic was initially present before the register file. So in the write back stage, before accessing the register file, it was present here. This multiplexer was present here, and the regdest selected which register I should write my data to, register RT or register RD. But as you remember from the previous tutorial, we told you that its presence here will cause a problem, because in a single cycle implementation, I have no problem. I have one instruction that will pass by all stages. So actually, the instruction that was decoded in the decode stage in a single cycle implementation and decoded the values of RT and RD will be the same instruction that is trying to write back its data to the register file. So actually, I could select from the decoded RT and RD numbers or register numbers. But in a pipeline implementation, while I'm trying to write back my result of an instruction to the register file, a totally different instruction is present in the decode stage trying to decode the values. So actually, if I kept this multiplexer here and it took its input from this if/id pipeline register, then it is going to take the input of the what? The RT and the RD of the instruction trying to be decoded, and not the instruction that is trying to write back its data. That's why we told you in the previous tutorial, we are going to pass by the write register value or the write register number to all pipeline registers till I reach the mem/writeback pipeline register. And when I reach the writeback stage of a certain instruction, I'm going to choose the write register or retrieve the write register number from the mem/writeback register. So this logic is now implemented in the execute stage. Okay, the multiplexer that will select whether I'm going to take RT or RD is now present in the execute stage rather than performing it in the writeback stage. Okay, and as you can see, the regdest is now being used in the decode stage as a control signal, and the output of this multiplexer will be the destination register I want to write my data to in the writeback stage of this instruction that is present now in the execute stage. And the destination register, whether it is going to be RT or RD, will be stored in what? In the EX/mem pipeline register. Okay? So these were the three control signals I needed to use in the execute stage. All other remaining control signals will then be passed to the EX/mem pipeline register, and I will get rid of what? Of the execute control signals. Okay, so I will no longer store these three control signals to the next pipeline register because I already used them, so I do not need them anymore, and I will only store or pass the control signals that will be needed for the memory stage and the writeback stage to the next pipeline register, which is the EX/mem pipeline register. As you can see here, what are the control signals needed in the memory access stage? So we finished the execute stage, now we went to the memory access stage. The memory access stage will retrieve its data from the EX/mem pipeline register and will also retrieve the control signals needed in this stage from the EX/mem pipeline register. As you can see, I will need the branch signal. If I'm a branch instruction, the branch signal will be 1, otherwise it will be 0. So actually the logic determining whether I'm going to take the branch address calculation I performed in the execute stage or whether I'm going to take the PC+4 is calculated in the memory access stage. So actually the logic of ANDing the 0 flag with the branch signal is performed in the memory stage. As you remember, the 0 flag was the result of the ALU operation. If it is 0, the 0 flag will be 1. Otherwise, if the result is not 0, the 0 flag will be what? Will be 0. So this logic is performed in the memory access stage. So I need to retrieve the branch signal from the EX/mem pipeline register to perform this logic. Also, the memwrite and the memread control signals are needed. So I can access the data memory. If I'm going to write to the data memory, I need to have the memwrite with 1. And if I'm going to read from the data memory, I need to have the memread with value 1. Or if I'm not going to perform any operation in the data memory, both control signals will be zeros. So actually I need to pass the value of the memory write and the memory read control signals because they are needed in the memory access stage. After finishing this stage, I'm going to pass the last control signal needed in the upcoming stage, which is the writeback stage, to the mem/writeback pipeline register. And the only control signal we now need in the writeback stage is the mem-to-reg control signal, which will determine whether I'm going to store in the register file the value of the data memory I read from the data memory or the value of the ALU result. As you remember, I can store in the register file in the writeback stage either a value loaded from the data memory or the value of an arithmetic operation performed in the ALU. So this control signal will tell me which value to store in the register file. So we have the mem-to-reg control signal which will select this value. Also, as you can see, the ANDing of the branch signal with the 0 flag will result in a control signal called the PC source. And this PC source is not generated from the control unit. It is generated from ANDing the branch signal with the 0 flag. And this PC source will tell us whether we are going to take the PC+4 or we are going to take the branch address value and update the PC with this value. And actually in your project you need to also implement the jump logic. So the control unit will have a jump signal, or the control unit will generate a jump signal, and we'll have here another multiplexer after this multiplexer. The new multiplexer will take the value resulted from this multiplexer, which selected between the PC plus 4 or the branch address value, and the second multiplexer will take this result and will try to choose between this result and the jump address calculation we performed, having the jump control signal as the selection line. Whether if the jump is 1, I'm going to take the jump address or update the PC with the jump address value. Otherwise, if the control signal jump was 0, I'm going to update the PC with the value chosen from this multiplexer, whether it was PC plus 4 or the branch address. So as you can see, the control signals are also stored in the pipeline registers. In the id/ex pipeline register, I store all control signals generated from the control unit. Then starting from the ex/mem pipeline register, I will only store the data needed by the next stages. So actually here in the execute stage, I used the execute control signals or the control signals needed in the execute stage, and I will discard them and I will not store them in the next pipeline register. In the next pipeline register, the ex/mem register, I will only store the control signals needed in the data memory or the memory access and the write back stages. And after I finish the memory access stage and use the control signals needed in this stage, I will discard them and I will only store in the mem/write back pipeline register the control signals needed for the write back stage. And also in this modified data path, we moved the multiplexer that selects the register destination, or which register I will write my data or I will write my result to, from here before the register file in the write back stage to the execute stage. Because let's assume I have an instruction, an add instruction, that one wants to write the result in the register file, so it is in its write back stage, while I have a subtract instruction in the decode stage. If actually this multiplexer was here and took the data from this if/id pipeline register, then the RT and the RD values or register numbers will be of the subtract instruction, and therefore the regdest signal was going to select the RT or the RD of the subtract instruction, not of the add instruction. Therefore, we moved this multiplexer to the execute stage and we performed the register selection, whether I'm going to save my data in the RT register or in the RD register in the execute stage, and this result will be passed by all the other or all the upcoming pipeline registers till it reaches the mem/write back pipeline register, where in the write back stage I'm going to take the register number and pass it to the write register field of the register file, while I'm also going to pass the write data from this multiplexer, which selects the data, whether I'm going to take the data from the data memory or from the ALU result and pass it to the write data field to be written in one of my registers, which is the register specified in the write register field or port. Okay, and this is implementation you are going to implement in the project. So now let's move on to a different concept, which is the introduction of a forwarding unit in our MIPS data path implementation. So if you remember in the previous tutorial, when we talked about data hazards arising from R-type instructions, for example, I have two instructions and the second instruction needs the result written in the first instruction. For example, if we had two addition instructions, instruction 1 is an add instruction and instruction 2 is another add instruction. Instruction 1 writes its result in register T1 and instruction 2 reads its values from register T1. So instruction 2 should actually have or read the new or updated value of register T1, which is written in instruction 1. So here comes a read after write or a row dependency. Instruction 2 is reading a data after it was being written in instruction 1. This dependency results in data hazards. And in the previous tutorial, we tackled how to solve data hazards from a software perspective. And it is really important. In the previous tutorial, we tackled how to solve data hazards from a software perspective. how to implement stalls or no operation, which is the NOP instruction, from a software perspective. Either the software developer or the programmer will manually detect the hazard and will write NOP instructions in the code, or the processor from a software perspective will automatically insert the NOP instructions or the NOP instructions or the no operation instructions to stall the pipeline before actually starting to what? To execute the code on the actual or physical hardware. Both techniques were done from a software perspective. In this tutorial, we will introduce a hardware solution, which is creating a forwarding unit in what? In our data path. So also in the previous tutorial, we tackled forwarding and we stated how do we perform forwarding. For example, instead of stalling, because stalling is very expensive, as I told you before, I can forward the result once it is ready to the component that needs the result in the following instructions. So instead of waiting for the write back stage to write back the data and the decode stage to decode the newly written back data, why not just, if the data is finished in R-type instructions after the execute stage at clock cycle X, why not pass it to the next execute stage, which is at clock cycle X plus 1, which is of the second instruction. So if I have two instructions, consecutive instructions, and the second instruction depends on the result of the first instruction, I can forward the result of the first instruction to the second instruction from the execute stage to the execute stage. From the execute stage at clock cycle X, which was executing instruction 1, to the execute stage of instruction 2 at clock cycle X plus 1. And we introduced the forwarding concept and the bypassing concept, meaning that I will bypass the values I decoded and I will take as an input parameter the forwarded value. You can check the previous tutorial if you still did not understand this recap. But actually, the hardware implementation is a lot better and the forwarding technique is a lot better than doing stalls from the software perspective. And actually, there is a stalls perspective or a stalling technique using hardware, which we will discuss later in this tutorial. But I wanted to make sure that you guys understood that the stalling of inserting no operations was a software level. You either manually insert the no operations or the processor will insert the no operations before the execution of the entire program. It will detect dependencies before what? Before executing the program. There is a totally different technique for stalling, which is implemented in the hardware level during runtime, not during compile time, but during runtime, which is a hardware implementation we will tackle later in this tutorial. Nevertheless, the forwarding approach is definitely a better approach compared to stalling from a software level or stalling from a hardware level. And that's why we will introduce one of the hardware techniques, but it is not for stalling, it is how to implement forwarding. So consider the following assembly code. I am adding the value of S0 to the value of S1 and I'm storing them in register T1. And actually we are tackling data hazards in R-type instructions. Okay, we are not tackling I-type instructions. This is for R-type instructions. So my register destination is register T1. The second following instruction or the second consecutive instruction is add the value of register T1 to the value of register S2 and store it in register T2. So actually my RS register is T1 and in instruction 2 I should have the new or updated value of register T1, which was calculated in the previous instruction or instruction 1. So here at instruction 2 I need to operate on the new value and therefore we will perform forwarding. There are some conditions for forwarding that must be met, meaning that I will introduce a forwarding unit that handles the forwarding logic. What is the forwarding logic? How can the data path during runtime know that there is an instruction that depends on the value of the previous instructions? Okay, this is done by the forwarding unit and some logic behind the forwarding unit. So, as I told you, what will happen is that at the execute stage of instruction 1, it should forward the result of T1 to the execute stage of instruction 2. So if this was at clock cycle 3, the execute of the second instruction will be at clock cycle 4. So I need to forward from clock cycle 3 to clock cycle 4 the new value of T1. So at clock cycle 4, the second instruction will be in its execute stage, and therefore it will operate on the value forwarded from the previous instruction, and it will bypass or discard the value it decoded in the decode stage. So this is the first forwarding condition we have. I mean, how will the data pass know that it needs to forward data? It needs to have a forwarding unit which performs some conditions or some logic to determine whether it needs to forward data or not. And this is the first condition, which is I am checking if register RS of instruction n plus 1 is equal register RD of instruction n, meaning register RS of instruction n plus 1 is this one, is register T1. I'm checking if it is equal to the register RD of instruction n. So instruction n is instruction 1, instruction n plus 1 is instruction 2. I'm checking is RS here equal RD here, is my source register here the destination of the previous instruction or not. This is my first condition, and it is performed as follows. I am checking if id/ex.register rs is equal ex/mem.register rd. The id/ex and the ex/mem are the pipeline registers. I mean, how can I know or how can I compare the values? Where are the values? The values are stored in the pipeline registers. The number of the register RS and the number of the register RD are stored in the pipeline registers. So if I go back, I can find that what I am checking here is the register in the id/ex, which is what register RS is equal to the register RD present in ex/mem. So if I'm having register number 9, is here RS equal 9 and here RD equal 9, is RS equal RD? Yes or no? If they are yes, then this is a forwarding condition and I need to what? To forward. So as you can see, I checked whether register RS in the id/ex pipeline register is equal to register RD in the ex/mem register. Is the register RS of instruction n plus 1 equal register RD of instruction n? Is my source register in instruction n plus 1 equal the destination register of instruction n? So as you can see, I am checking here in id/ex the register of what? Register RS is equal to the number of register RD in ex/mem, because actually when instruction 1 is in the execute stage and it finishes execution, it will store its data in the ex/mem pipeline register, while instruction 2, which was in the decode stage, will store its data in the id/ex register. Okay, so I'm comparing the register RS of instruction 2, which is now stored in id/ex, with the register RD of instruction 1, which is stored in ex/mem. And this is the first part of condition 1, which is called 1a. And it is really important to know that this is called condition 1a, because we have what? We have a second condition for 1, which is what? If my source register is in register RT, not RS, like this assembly code, I am performing the same addition, the value of S0 plus the value of S1, and I'm storing it in register T1, so my destination RD register is T1. But in instruction 2, I am performing the value of S2 plus the value of T1 and storing them in T2. So now T1 is not my RS. T1 is what? Is my RT register. So I need to perform the same condition here, which is condition 1b. If the RT of instruction n plus 1 is equal RD of instruction n, it is same as the previous condition, but I'm replacing RS with RT, because actually when I read, I can read either register RS or register RT. I have two operands and both can have what? Can be RD of the previous instruction. So I'm checking in the pipeline register id slash ex dot register rt is equal ex slash mem dot register rd. So here I'm comparing, is register rt equal register rd? Register rt of instruction n plus 1 is equal register rd of instruction n. It is the same condition as the previous condition, but we are replacing register rs with rt. We are now checking for the second operand. In the first condition, we checked on the first operand, which is register rs. The dependency may occur on the second operand. We may have a read after write, a row dependency on the second operand. Rt is equal rd. That's why we are checking here the rt of the current instruction is equal to the rd of the previous instruction or not. So if we go back to the data pass, at id slash ex pipeline register, I have two registers, rs and rt, the two operands that I will perform on them an ALU operation or an arithmetic operation. I am checking whether rs is equal rd, which is stored at ex slash mem, or rt is equal rd, which is stored in ex slash mem. These are the two pairs of condition for the forwarding condition 1, which is having two consecutive instructions. Instruction 2 needs the value of instruction 1. So I'm checking whether the two operands rs and rt are of the currently or of the current instruction are equal to the destination rd of the previous instruction or not. So if we go back to the data pass, here in ex slash mem, it will contain the data of instruction 1, while id slash ex will contain the data of instruction what? Instruction 2. So rs and rt here of instruction 2 and rd here is of instruction 1. That's why I'm comparing rs of instruction 2 to rd of instruction 1 and rt of instruction 2 with rd of instruction 1. And this is performed here because here will reside the forwarding unit. As you will see later, the forwarding unit will be present in the execute stage because actually I will have the result that I want to forward from the execute stage. That's why I have the logic of the forwarding unit implemented here, and therefore it will check whether there are dependencies between the instruction in ex slash mem and the instruction in id slash ex or not, a read after write dependency. Okay? And we tackled the two pairs of the forwarding condition 1 when we have two consecutive instructions depending on each other, and therefore a data hazard will occur. And this is for R-type instructions. There is another condition for data hazards in R-type instructions, like this example. Consider the following assembly code. In the first instruction, it is simple. I am adding S0 and S1, and the result is stored in T1. So my RD is T1. In the second instruction, it's a normal instruction. I am storing S2. I'm adding S2 to S3 and storing the result in T2. No dependencies here because I am reading S2 and S3, which are independent of any previous register used. But here in instruction 3, I have a problem, which is T1 plus S1, and then it will be stored in T3. And during instruction 3, the new value of T1 will not be written yet. I mean, when instruction 3 tries to decode the value of register T1, still instruction 1 did not write it back to what? To the register file. Therefore, we will have a data hazard, and this add instruction will retrieve the old value of register T1 from the register file because it did not have time for this instruction to finish what? To finish its write back. Okay? Because when this instruction 3, will be in the decode stage, instruction 1 will be in the memory access stage and not in the write back stage. Therefore, the new value of T1 will not be written yet. And as you can see here, the dependency is that register RS is T1. So we have a dependency between RS and RD, between instruction 3 and 1, a read after write or a row dependency that will cause a data hazard. So we can deduce that we have another pair of what? Of conditions, which are the forwarding conditions 2. So I'm checking here if register RS of instruction n plus 2, here not n plus 1, now we're checking n plus 2, is equal to register RD of instruction n, which is if the id slash ex dot register rs is equal to the mem slash write back dot register rd, and this condition is called 2a. So here I'm checking is the rs of instruction n plus 2, which is instruction 3, is equal to the register rd of instruction n, which is instruction 1. So I'm checking is the rs of instruction 3 equal the rd of instruction 1 or not. Okay, this is done in the pipeline registers as follows: id slash ex dot register rs equal mem slash write back dot register rd. So if we go back to the data path, we can see that I'm checking here the id slash ex, the value of register or the number of register rs here, which is instruction n plus 2, is equal to the number of register rd, which is in instruction n, which is now at mem slash write back register. So instruction 1 will be finishing its memory stage and its data will be stored in the mem slash write back register, while what? While instruction n plus 2 will be finishing its decode stage and its rs and rt values will be in id slash ex pipeline register. So now I'm checking that the values here of instruction n plus 2, rs and rt, but in the first condition 2a we are only checking for rs, is equal to here the mem slash write back register rd of instruction n. I'm checking if they are equal or not. The source here or the first operand here is equal to the destination here. That's why we checked id slash ex dot register rs is equal mem slash write back dot register rd, and this is the first half or the first part of the pairs of forwarding condition 2. We are checking now for dependencies between instruction n and n plus 2. Is the rs of n plus 2 equal the rd of n or not? And that's why we have what? The second part or the second half of the forwarding condition. It is the same example. I'm storing S0 or I am adding S0 plus S1 and storing them in T1 in instruction 1. Therefore, register RD is equal T1. Instruction 2, we have no dependencies. We are adding S2 plus S3 and saving them or saving the result in register T2. So no dependencies. S2 and S3 are not being used beforehand. Now the dependency occurs in instruction 3. I am adding the value of S2 plus the value of T1 and storing it in register T3. Therefore, the RT is now T1. In the previous example, the RS was T1, which was the first operand. Now no, the dependency, the read after write dependency is on the second operand, which is the register RT. Therefore, I have a dependency because RT here is equal RD here. The RT of instruction 3 is equal to the RD of instruction 1. Therefore, we have what? The second condition, which is 2b. The second half of forwarding condition 2. I'm checking if register RT of instruction n plus 2 is equal to register RD of instruction n. So, in terms of pipeline registers, the id slash ex dot register RT is equal to the mem slash write back of register RD. So we replaced RS with what? With RT, because the operand can be either source 1, which is RS, or source 2, which is RT. We have two operands and I can have a dependency in any. RD may be equal to RS or may be equal to RT. So if we go back to the data path implementation, we can find out that here at id slash ex, which contains instruction n plus 2, I am checking whether RS and RT are equal to the destination register RD of instruction n, which is residing in memory slash write back register or not. Because as I told you, the pipeline registers store the data and operands and control signals of the instructions. So if I want to perform some comparison or some logic, I need to retrieve the data first from the pipeline registers. Therefore, I'm taking here or retrieving the register RD from mem slash write back and comparing it with what? with the RS and the RT inside the ID/EX. And as you all deduced, both conditions, forwarding condition 1 and forwarding condition 2, must be checked to check for or detect dependencies. Okay, so I know whether I need to perform forwarding or not, meaning that I have 3 instructions. N will be at memory/write back, meaning it is in the data memory stage. Instruction n+1 will be at the ex/mem pipeline register, which means that it was in the execute stage. And finally, instruction n+2, which will be in the ID/EX pipeline register, meaning it finished the decode stage. I need to check first whether instruction n+1 RD is equal to the RS and the RT of instruction n+2 or not, and at the same time I need to check the RD of instruction n, which is from the memory/write back stage, is equal to the RS and the RT of instruction n+2, which is in the ID/EX stage. So actually I'm going to compare mem/write back with ID/EX and EX/mem with ID/EX. Here destination, here RS RT, here are also destination, which is RD, here RS RT. Okay, so I'm going to perform both conditions, condition 1 and condition 2 for forwarding, and I'm going to check, because definitely we'll have a program with many instructions and any dependency can occur. I may have 2 consecutive instructions having a dependency like n+1 and n+2, or I can have a difference of 1 instruction in between, like n here and n+2, having an instruction in the middle that does not have any dependency. So I need to check for both conditions. So let's move back, and here we tackled both pairs of forwarding condition 2. Now here is the data path containing the forwarding unit. It is a very simple data path, not the full implementation or the modified implementation. And as you can see here, we introduced the forwarding unit in the execute stage. Okay, so forwarding occurs in the execute stage for R-type instruction. I'm repeating, we are tackling data hazards for the R-type instructions. And as you can see, we have here the forwarding unit, which takes as an input parameter what? The RS and the RT from ID/EX. So I have the ID/EX pipeline register. It will always provide to the forwarding unit the register numbers of RS and RT. Meanwhile, the EX/mem pipeline register will provide the register number of RD, and the memory/write back pipeline register will provide the register number for what? For RD. So here I'm getting RD from EX/mem, here I'm getting RD from mem/write back, and here I'm getting RS and RT from ID/EX. And both forwarding conditions, condition 1 and condition 2, will occur at the same time inside the forwarding unit, whether it is 1A and 1B or 2A and 2B. So now we introduced the forwarding unit and what are the input parameters to the forwarding unit. Let's move on to what the other modification that occurred in the data path. As you can see here, we have what? We have our ALU, but instead of having the values coming or going directly to the ALU, we introduced 2 new multiplexers. A multiplexer with selection line called forward A and a multiplexer with a selection line called forward B. And take care, forward A is 2 bits because it is selecting between 3 values, and forward B is also 2 bits because it is selecting from what? From 3 values. So I need 2 bits to select between 3 values. And forward A and forward B selection lines are the output of the forwarding unit. So the forwarding unit output 2 selection lines, forward A, which is 2 bits, and forward B, which is also 2 bits. Forward A will select the first operand to the ALU. Forward A will select the first operand to the ALU, while forward B will select the second operand to the ALU. So, as you can see here, the first multiplexer, the first input to the multiplexer is the value coming from the ID/EX pipeline register, which means that this is the value that was decoded in the decode stage. I mean, in the decode stage, I read the register file and I retrieved a value from the register file. This value is stored in the id/ex pipeline register, and then it is being used as the first input to the multiplexer. Okay? Now, the second input to the multiplexer, if we trace this line, we will find out that it is coming from this multiplexer. And as you can see, this multiplexer gets its values or selections, whether it will select the result coming from the data memory if it was a load instruction, or the earlier ALU result of this instruction. And the multiplexer will select whether you want the value from the data memory or the earlier ALU result. Therefore, the second input to this multiplexer, which the multiplexer will choose one of the three inputs, is coming from what? From the write back stage, which is mainly coming from the memory/write back pipeline register. Because in this multiplexer, it is just going to what? To pass one of the two values, the load value, or loaded from the memory, or the ALU result value. But mainly it is as if it is retrieving the value from the memory/write back register. Finally, the third input that the multiplexer will select from is coming from where, if we trace the line, we will find out that it is coming from the ex/mem pipeline register, which is the ALU result of the previously executed instruction. So in the previous instruction, I had an ALU operation, and thus its result is stored in the ex/mem pipeline register. So I can retrieve this value from this pipeline register. Okay, so as if the first line always will be the data decoded and read from the register file, as if it's a normal operation, no forwarding needed. The second line will take the data from the memory/write back register, and the third line will take data from the ex/mem pipeline register. Okay? Same goes to the second multiplexer, exactly the same order. The first line will get data from the register file, the second line will get data from the mem/write back pipeline register after the multiplexer of the write back, and finally here we will get the third line will get the data from the ex/mem pipeline register. Now let's see the different combinations for both selection lines, and let's start with forward A. If forward A value is 0, 0, therefore it will pass the id/ex pipeline register value, which is the first line. So if I choose 0, 0 in forward A, I'm going to pass the value from the register file, which is from what? The id/ex pipeline register. The first ALU operand comes from the register file. As I told you, 0, 0 in forward A, so the first ALU operand will come from the id/ex pipeline register, which is the value from the register file, the normal decoded value. If the forward A is equal to 1, 0, it will retrieve the data from the ex/mem pipeline register, meaning the first ALU operand forwarded from previous ALU value. And here comes forwarding. In 0, 0, I had no use for forwarding. I did not implement forwarding. I did not need or use forwarding. Here I am what? I am using forwarding. I'm forwarding some data from the ex/mem pipeline register to the ALU as a first input or a first operand. Therefore, as you can see, if forward A here was 1, 0, then it will select the third line. Alright, do not get confused. 1, 0 is the third line. The third line is what? Is the data from the ex/mem pipeline register, which is this. Okay, as you can see, this line is the third line in the multiplexer, which will choose the data from the ex/mem pipeline register to be the first operand to the ALU. So the first one is 0, 0. The last one is what? Is 1, 0. So it makes sense the one in the middle will be what? Will be definitely 0, 1. That's why forward A, if it is 0, 1, the source will be mem/write back pipeline register. I'm going to get the value of register RS from the mem/write back pipeline register. the first ALU operand forwarded from data memory or an earlier ALU result, depending on the last multiplexer, whether this will pass value from the data memory or the previous ALU result. So if I choose here 0, 1 for forward A, the value of register RS, which is the first operand, will be retrieved from memory / write back pipeline register. So as a recap for forward A, if forward A is 0, 0, then register RS will be the normally decoded value or register from the register file. Okay, I read value from the register file, I stored it in the ID/EX pipeline register, it will be the normal RS value, no forwarding needed. But if I choose here 0, 1, 0, 1 for forward A means I need to forward from the mem/write back pipeline register. So forwarding is needed, and this is the case of what? That n plus 2 is equal n. The register RS of n plus 2 is equal the register RD of n. So I need to get the value of register RD from the mem/write back pipeline register. Therefore, it will be forwarded, and thus the RS will be the value of RD from the mem/write back pipeline register. Finally, if forward A is equal to 1, 0, then the value of register RS should be equal to the value of register RD from the EX/mem pipeline register. So I have two consecutive instructions. Instruction n plus 2 RS is equal to the RD of instruction n plus 1, which is an EX/mem pipeline register. So I need to get the value of RD and let the value of RS become the value of RD from the EX/mem pipeline register. Therefore, RS will be what? The value of RD from the EX/mem pipeline register if forward A is 1, 0. So now we are done with forward A. Forward B exactly follows the same concept of forward A and with the same values. So if forward B is actually 0, 0, meaning that the second ALU operand will come from the register file. So I'm going to take the value from the ID/EX pipeline register. If we go back to the data path, we can see that forward B 0, 0, it will select the first input, which is coming from the ID/EX pipeline register, which is no forwarding is needed. I'm going to take the normal value from the register file for the second ALU operand, which is register RT. Now, if forward B is 1, 0, the second ALU operand will be forwarded from the previous ALU value, and the previous ALU value is stored in the EX/mem pipeline register. So if we go back, forward B becoming 1, 0, it will select the third line. Take care, it will not select the second line. 1, 0 selects the third line, and the third line gets the value from the EX/mem pipeline register. Therefore, this means that instruction n plus 2 RT is equal to the RD of instruction n plus 1, which is in the EX/mem pipeline register. Therefore, I need to take the value of RD from the EX/mem pipeline register and pass it to the second input to the ALU, or to be the second operand to the ALU, to be the RT of the ALU. Okay, if the forward B is 1, 0. The last case is what? That forward B becomes 0, 1. Therefore, the second ALU operand forwarded from the data memory or an earlier ALU result, meaning that we will forward the value of RD from the mem/write back pipeline register to become the second ALU operand, which is the RT. So if we go back, forward B becoming 0, 1, meaning I'm selecting the second line. The second line is what? Is getting the data from the mem/write back pipeline register. Okay, so this means that the RT of instruction n plus 2 is equal to the RD of instruction n, and therefore I need to forward the value of RD from the mem/write back register to what? To become the second ALU operand for the ALU, or to become the value of RT. Okay, so again 0, 0 will take normally, no forward needed. I will take normally the value retrieved from the register file, which is in the ID/EX pipeline register. If the forward B is 0, 1, I'm going to take the value of RD from mem/write back register to become the second ALU operand. If the forward B is 1 0, I'm going to take the value of the ex slash mem, the rd of the ex slash mem, to become the second operand for the ALU. So now an important question arises, which is, do we always forward, meaning that if the conditions satisfied, the forwarding conditions, we have 4 forwarding conditions, 1A, 1B, 2A, and 2B, any one of them is satisfied, will I always forward if one of these is satisfied, or there are some scenarios or situations where actually one of these conditions will be satisfied, but it is useless for me to forward? The answer to the question, do we always forward, is no. We do not always forward even if one of the 4 conditions for forwarding is satisfied. So we have some conditions, even if one of the 4 conditions of forwarding is satisfied, the instruction that will forward the data must also satisfy some other conditions. So you only forward if the instruction that is going to forward, I mean the instruction that is going to forward its RD data to become one of the 2 operands of the next instruction or the upcoming instruction, have the following conditions. The reg write control signal is 1, meaning that if I have an instruction that is actually going to forward its data, we need to make sure that actually this instruction will save its result in the register file in the first place. Just imagine if this instruction will not save its result. Its reg write control signal is not 1, it is 0. Okay, meaning that it will not update the value of any register in the register file. Therefore, the instruction that actually we found out that there is a dependency and a hazard will not need to have a new value to use it as an operand, because it can directly retrieve the old value from the register file, because the instruction, the previous instruction, will not actually update the value. Okay, so we need to make sure that the instruction going to forward the data will actually in the first place store the result in the register file. And how to know that it is going to store the result in the register file or not? Checking on the reg write control signal. If it is 1, meaning it will write data to the register file. At the same time, we need to make sure that the 0 register is not the destination register of this instruction. Meaning if I'm performing an instruction, an addition, and my destination is the 0 register, which is a hardwired register containing the value 0, it's a read-only register with the constant value 0, I cannot overwrite the value inside the 0 register. Therefore, if actually the instruction that is going to forward the data, its destination is register 0, it does not make sense, because it can never write to register 0 any new value. Therefore, no need for forwarding. I can just retrieve the old value from the register file, because no new value will be written. I cannot write on register 0. So I need to make sure about 2 things. That the reg write control signal is 1, the instruction that is going to forward the data is actually saving the result to the register file, and that the destination of this instruction is not register 0, because I cannot write a new value or overwrite the value of register 0. So as you can see, if we did not have these conditions ended together, we may actually forward a wrong value. Just imagine I am adding 4 plus 5 and storing at register 0, and we have a dependency that I want to read the value of register 0. If we did not have the second condition, for example, what will happen? I will try to forward the result of 5 plus 4 to the instruction that is going to read the value of register 0. But guess what? I cannot update the value of register 0. Therefore, I am going to forward a wrong value, because the value of register 0 is always 0. So you can, as you can see, I may even forward wrong values. Therefore, we have these 2 conditions to prevent the forwarding of wrong or useless values. So if we want to update our conditions, the forwarding condition 1, we will have 1a is if ex/mem.regwrite, meaning that regwrite equal true, which is equal 1. I mean, if it is true or regwrite value is not 0, it is 1, thus it evaluates to true. If it is 0, it evaluates to false. So if I say if reg_right, meaning that if it is true, if reg_right is equal true. So if reg_right is equal true, which is having the value 1, and the ex/mem.register_rd is not equal to 0, so here I'm doing both conditions. As you can see, the reg_right is 1, and we have here an and, the register RD is not equal to 0. Then we have and our old conditions where the id/ex.register_rs is equal to the ex/mem.register_rd. So as you can see, we are here checking on the ex/mem pipeline register. If I'm going to forward the value of ex/mem pipeline register, I need to make sure that the ex/mem pipeline register RD is not equal to 0, the register number 0. Register 0 is actually register number 0. Therefore, I'm checking on number 0, and at the same time, the reg_right control signal is 1. Then I will forward, and forward A will be 1, 0, as you recall from the previous slides. Condition 1b, I'm performing the same thing. If ex/mem.reg_right is equal to true or equal to 1, and ex/mem.register_rd is not equal to 0, so I'm making sure register right control signal is 1 and the destination is not register 0. And I'm performing the old condition, which is id/ex.register_rt. Now I'm checking on what? On the second operand is equal ex/mem.register_rd. So here I'm checking on what? n+2 and n+1. I'm making sure in both conditions that if rs or rt of n+2 is equal to the rd of n+1, so I'm having two consecutive instructions, I need to make sure of two things: that the register right of the instruction n+1 is equal to 1, and the register destination rd of instruction n+1 is not register 0. Therefore, the only addition I added was this line, the first line in 1a and in 1b, making sure that the reg_right is 1. Therefore, I wrote if ex/mem.reg_right. I mean, writing if ex/mem.reg_right alone means that the reg_right is true, which is not 0, it is 1. And I'm making sure register RD is not register 0, and register 0 is numbered 0. If you remember the numbering of the registers, register 0 is equivalent to register number 0. So in condition 1b, finally, I will use forward B will be 1, 0, because forward A is concerned with register RS, the first operand, while forward B is concerned with register RT, the second operand. Okay, so if I have a problem with RS, I'm going to select using forward A. If I'm having a problem with RT, I'm going to select with forward B. So here the forwarding conditions are straightforward. I'm having the previous forwarding conditions, making sure the RS of instruction n+2 is equal to the RD of instruction n+1, or the RT of instruction n+2 is equal to the RD of instruction n+1, and at the same time I'm making sure that instruction n+1, its reg_right control signal is 1, meaning that the value it calculated in the execute stage will actually be written to register RD in the register file, and at the same time that the register RD is not register 0 because I cannot overwrite register 0. Moving on to the forwarding condition 2, now I'm checking on instruction n+2 with instruction n. So I'm checking that if memory/write back for 2a dot reg_right, meaning that the reg_right value is 1, and mem/write back dot register RD is not equal to 0, meaning that my destination register RD of instruction n is not register 0, and the id/ex.register_rs is equal to the mem/write back dot register RD. So the RS register of instruction n+2 is equal to the RD register of instruction n. Therefore, forward A will be 0, 1, meaning you need to forward the data from the mem/write back pipeline register. Unlike the previous example, the forwarding condition 1, when we forwarded from what? From the ex/mem pipeline register. But in forwarding condition 2, we will forward from the mem/write back pipeline register. And since we are concerned with register RS, we updated the forward A selection line. The second condition 2B, if mem/writeback.reg_write, meaning that the reg_write is 1, I'm going to write to the register file, and mem/writeback.register_rd is not equal to 0, meaning that my destination register is not register 0, and id/ex.register_rt is equal mem/writeback.register_rd, meaning that the rt of instruction n plus 2 is equal to the rd of instruction n. Therefore, I need to forward the data from the mem/writeback register to what? To the ALU as a second operand, because we are concerned with register RT, so I'm selecting forward B equals 01. It will take the data as a second ALU input from the mem/writeback pipeline register. So, similar to the previous slide, the second condition is the normal condition we tackled in the previous slides. The new condition is what? I am making sure that the reg_write is 1, it will write to the register file, and at the same time, therefore there is an AND. Take care, it's an AND, not an OR. And make sure that both conditions are satisfied. If this is true and this is true, if the reg_write is 1 and the destination is not 0, if one of them is false, then it's entirely false. Making sure the register destination is not 0, and then we continue with the normal conditions, the normal 2A and 2B. So we have two main forwarding conditions, condition 1 and condition 2, with a total of 4 conditions, because condition 1 has 1A and 1B, as you can see, whether register RS or register RT, and condition 2 is 2A and 2B, whether register RS or register RT. So actually we have 4 conditions for forwarding, in general or in total. So now let's move on to some questions regarding the forwarding unit. So consider the following assembly code. I am adding the value of T1 to the value of T2 and storing it in T1, that's instruction 1. Then in instruction 2, I am adding the value of T1 to the value of T3 and storing it again in register T1. Then in instruction 3, I am adding the value of T1 to the value of register T4 and storing it in register T1. So as you can see, we have multiple dependencies, okay? Instruction 1 is writing to register T1 and instruction 2 is reading from register T1. So we have a hazard between 1 and 2. And then between instruction 2 and 3, I'm also having a hazard. I am writing to register T1 in instruction 2 and I want to read from register T1 in instruction 3. But now we have a very huge problem regarding instruction 3, which is having the 4 conditions for forwarding 1A, 1B, 2A and 2B. 2 conditions will be triggered for instruction 3, because as you can see, instruction 3 RS is T1 while instruction 1 RD is T1, and this will trigger the condition of RS of n plus 2 is equal to the RD of n. And at the same time, I'm having what? I'm having the RS of instruction n plus 2 is equal to the RD of instruction n plus 1. So 2 out of the 4 conditions will be true, and we will have a collision, a clash will occur. Should I forward the value of instruction 1 or should I forward the value of instruction 2? Because 2 conditions are satisfied. N plus 2 RS is equal to n plus 1 RD, and at the same time, n plus 2 RS is equal to what? N RD. Therefore, 2 conditions out of the 4 are true. Which value should be forwarded? Logically speaking, we should forward the value of instruction 2 because it is the most new value. It is the most updated value. So it makes sense to take the value of instruction 2 and forward it to instruction 3. So from where the result should be forwarded and why? As I told you, the execute stage, because it has the most recent value of T1. So I should forward the value from the ex/mem register, not from the mem/writeback register. Because if I go back, instruction 2 has the most recent value for register T1, the most updated value. So I should forward this value to instruction 3. I should not forward the value of instruction 1 to instruction 3, although its condition will be what? Will be satisfied. If we go back to the conditions, we can see here that this condition 2a will be satisfied. Rs of n plus 2 is equal to Rd of n. N plus 2 is in id slash ex and n is in mem slash write back. At the same time, Rs of n plus 2 is equal to Rd of n plus 1, since n plus 2 is in id slash ex and n plus 1 is in ex slash mem. So 1a and 2a will be true, but in reality I want to forward the data of what? The data of 1a. I do not want to forward the 2a condition because I want the most recent or updated value for register T1. That's why we should forward from the execute stage. The second question is, what might be implemented in the high-level source code behind the above MIPS code? Explain. So basically, it's trying to identify the functionality of this assembly code. If we see the solution, summing a vector of numbers in a single register. MIPS instructions are all reading and writing to the same register, which is T1. So the functionality is the summation of a vector of numbers in a register or a single register. As you can see, we are having register T1 and we always sum to this register. It's like having sum equal sum plus I, for example. So I'm actually reading the old value of register T1, adding to it a new value, and then summing it back or storing it back where in the same register, which is T1. So it's like you are writing a functionality that sums a list or an array of values. Okay, so what shall you do? You will create a variable called sum, and you will say sum equals sum plus array of index, and this array of index will always have what? A new value. So you are reading the old value of summation, adding to it the value from the array, then storing it back to the summation variable. And you will perform this until your loop finishes or ends. This is the same functionality. I am reading from a register, I'm going to add a value to this value that I read, and then I'm going to store back to this register. Then I'm going to perform the same functionality. We'll read the updated value, we'll add a totally different value to it, and then store it back to the same register. So it is the summation of a vector of numbers in a single register. Now let's update our forwarding conditions, especially forwarding condition 2, to prevent it from what? From forwarding when condition 1a is satisfied. So I have 1a and 1b. If 1a and 1b are satisfied, I should not look into what? Into condition 2a and 2b. And we will see in the previous example, we had 1a and 2a both were true. If 1a is true, then I should not forward or perform the functionality of 2a. I should only go for 1a, because 1a will forward from the execute stage. The most recent value will be stored in the execute stage. So as you can see here, this is forwarding condition 2a. It is exactly the same as in the previous slides. We only had one modification, which is adding an AND to it where 1a is equal false. So I'm having condition 2a, mem slash write back dot reg write. I'm making sure the reg write signal is 1, and mem slash write back dot register rd is not equal to 0. I'm making sure my destination is not equal to 0, and I'm making sure that the rs of n plus 2, which is in the id slash ex pipeline register, is equal to the mem slash write back dot register rd. Instruction n is in mem slash write back. I'm making sure the rd of instruction n is equal to the rs of instruction n plus 2. Also, I'm going to add this condition, which is that condition 1a must be false, because if condition 1a is true, I'm always going to what? To forward from the most recent value, and the most recent value will always be in the execute stage, which is the ex/mem pipeline register, which is tackled in condition 1a. Therefore, I need to make sure before forwarding the value from the mem/writeback pipeline register that actually the condition 1a is false. If it is false, then I am free to what? To forward the data from the mem/writeback register. But if condition 1a is true, meaning that the previous example here, 1a was true because there is a dependency between instruction n+1 and n+2, while 2a was true because I have a dependency between instruction n and n+2. I need to forward what? From instruction 2, which is in the ex/mem pipeline register. Therefore, I should not forward from the mem/writeback register, so I need to add an additional condition to condition 2a to make sure that condition 1a is false. If it is false, then I do not have a middle dependency here. Instruction 2 and instruction 3 will not have any dependencies, therefore I can forward from 1 to 3. That's why I'm making sure here that 1a is equal to false, which is what? Not 1a. I mean, I'm making sure 1a is equal to false is not 1a. So actually, if 1a is true, then not 1a will be false, and therefore ending it will result in this condition entirely becoming false. Otherwise, if 1a was false, then not false will be true, and therefore end true will make the condition continue. So if you want to break down not 1a, it will be like this. I'm adding a not, and then I'm adding what? The condition of 1a. The not will enter, so this will be that reg write, not reg write. This and will be or, rd will be equal 0. This and will be or, and this equal will be not equal. So it's like simple implementation, simple logic. The not entering, so it will switch every and equal and not equal to the opposite. If you are an and, you will become an or. If you are true, you will become false. If you are not equal, you will become equal. If you are equal, you will become not equal. Therefore, if this condition evaluates to true, not true will make it false. If this condition evaluates to false, not false will become what? Will become true. And this condition, starting from the red bracket till the red bracket, is the condition of 1a. So this entire red bracket, the expression inside the red bracket or the condition inside the red bracket corresponds to condition 1a. Okay, so forward a will be 0, 1 because we are tackling or concerned with register RS, so we are concerned with forward a, and 0, 1 means you are now allowed to forward the data from the mem/writeback pipeline register. The same occurs to 2b, okay, but 2b is concerned with register RT, so we are concerned with forward b. Here, if RT is equal to what? RT of the instruction n+2 is equal to the RD of instruction n. So we need to make sure that condition 1b is false. Okay, if we go back here, just imagine that this was not RS, this was RT. It was instead of T4. T1 was swapped with T4. Therefore, T1 is now RT. So we need to check the conditions 1b and 2b. So if we go back here, we need to make sure that condition 1b is equal false. It is similar to what we did in the previous slides. Okay, but here I'm concerned with register RT, not RS. Therefore, I'm concerned with 2b and 1b. So since this is condition 2b, I need to check on 1b being equal false, meaning that there is no dependency between the RT of n+2 and the RD of n+1. I only have dependency between the RD of n and the RT of n+2. Therefore, I'm making sure 1b is equal to false, which is not 1b, which can be later on. Breaking down not 1b, I will transfer this not notation into a not, and I will put the 1b condition. So this is the not and this is the 1b condition. Okay, and as you can see, I'm checking on what? On RT of n plus 2 equal to the RD of n plus 1, because the RT of n plus 2, if it is equal to the RD of n plus 1, and the reg write is 1 and the destination is not register 0, therefore I do not want to what? To forward from mem slash write back. I want to forward from execute slash mem. Therefore, I need to take the most recent value, which will be present in the execute slash mem. Therefore, if this evaluates to true, then not true will become false, and therefore I will not be able to continue the forwarding condition 2b. And therefore 1b will be the condition that will be passed or will be forwarded, and 2b will not continue because it will result in an overall of false. Since and not true, meaning and false, will make the entire expression, the entire condition false. Otherwise, I'm going to forward from forward B selection line, and I'm going to choose 01, which is the value from memory slash write back pipeline register. If this condition 1B evaluated to false, so not false will be true, and we will continue normally the forwarding condition of 2B, and we now can forward from the mem slash write back register if the rest of the condition is true. And we are forward B because we are concerned with register RT, the second operand to the ALU. Now we are done with handling R-type data hazards and their forwarding conditions. Okay, now let's move on to a different concept, which is the introduction of a hazard detection unit that performs hardware stalling. Okay, so as you remember, stalling is inserting no operations or NOP instructions which will stall the pipeline. We tackled in the previous tutorial how to insert NOPs from a software perspective. In this section of this tutorial, we will tackle how to create stalls or how to introduce stalls during runtime. When I am running my program on the hardware or on the processor, how will it detect that we have a hazard and we need to stall, and forwarding will not work? Because actually, if I need to stall, this means that forwarding is not working. I cannot solve a certain issue with forwarding, therefore I need to stall. And the most famous example for storing where forwarding will fail and stalling will succeed is the load data hazards. Therefore, we will tackle the data hazards, the load ones. Okay, in the previous section, we tackled the R-type instructions and the R-type data hazards, and their solution was easy. Introduction of the forwarding unit. But in case of load data hazards, forwarding is not efficient, forwarding will fail and it will not work, and we need to stall the pipeline. Consider the following assembly code. So I want to perform a load word instruction where I am retrieving some data from the memory and storing this data in register T1. And as you remember, register T1 here is the RT register, okay, because it is not the RS. The RS is the base address, which is registered as 0. The base address is stored inside register as 0, and I will retrieve this address from register as 0, add to it the offset, which is 0. This will be the address of the memory location I want to retrieve the data from. Instruction 2, I am performing an addition instruction. I am adding the value of register T1 to the value of register S1 and storing the result in register T2. Therefore, as you can see here, the RS register is T1. We here have a read after write or a row dependency. Because as you can see in instruction 1, I am writing to register T1, and instruction 2, I am reading from register T1. Therefore, I need to read the most recent or the updated value of register T1 during instruction 2. Here, we will not have the most recent value if we performed the normal operation of the data pass, because I need to retrieve the data from the data memory in the memory access, while in the normal situation we decode the values in the decode stage. So actually, when instruction 2 is in the decode, instruction 1 will be in the execute stage. Therefore, it will not have the recent value or the intended value. So we have here what? A data hazard. Okay, T1 will be loaded with the wrong value. Now we will check or see that forwarding will not be efficient, and actually forwarding will not work in this case. I cannot forward the data. Why? As you can see, I am fetching instruction 1 at clock cycle 1. That's normal. I am decoding instruction 1 at clock cycle 2, and I am fetching instruction 2 at clock cycle 2. That's normal. At clock cycle 3, the add instruction will be in the decode, while the load instruction will be in the execute. So as you can see here, I will try to what? To decode the values. No problem, the values, we may decode the wrong values. If we perform the forwarding technique, we actually take into consideration that we forward to the execute stage. We do not forward back to the decode stage. So yes, we perform forwarding and bypassing. So in the forwarding, we will always bypass the values retrieved from what? The decode stage. So I have here no problem. The problem occurs at clock cycle 4. The load word will be in the memory stage, while the add instruction will be in the execute stage. Now what will happen? In the memory stage, I'm going to retrieve the value from the data memory. At the same time, the addition instruction is performing an execution. Guess what? It is executing on wrong data, because I cannot forward from one stage to another in the same clock cycle. Okay, I can forward in the upcoming clock cycles. So I need to stall instruction 2 by one clock cycle. So its execute stage will become in clock cycle 5. So I can forward from the memory stage to the execute stage, from clock cycle 4 to clock cycle 5. But I cannot perform forwarding in the same clock cycle, because at clock cycle 4, I am still retrieving the data from the data memory. The data memory did not actually get me the data. I did not read the data. I am performing this operation of reading the data from the data memory at clock cycle 4. So the data is not yet ready in clock cycle 4. While in clock cycle 4, I'm trying to perform an execution, the arithmetic operation of the addition. So we have a problem. The data is not ready, and the addition is in what? Is in the execute stage. So I cannot forward. Therefore, forwarding will fail. And I can only forward from a clock cycle to the next clock cycles. I cannot forward in the same clock cycle because the data is not yet ready. Therefore, the only option here is to perform what? Is to perform a stalling instruction, or to perform a no operation. I need to stall the pipeline. And as we tackled in the previous tutorial, we stall the pipeline by inserting NOP instructions. And NOP instructions are high-level assembly instructions. So yes, you can write NOP as an instruction. The processor will understand it, because the processor will decompose the NOP instruction you wrote into shift left logical register 0, and 0, which means I'm trying to shift the value of register 0 by 0 and store it in register 0. So it is nothing will occur in the data pass. No values will be changed, because I cannot overwrite the value of register 0. So, and this is predefined. I mean, the no operation corresponds to this shift left logical. The designers of the MIPS architecture decided so. It's not our decision. It is the designer's decision. Okay? So as you can see, we need to stall by one clock cycle. So this add instruction, it will execute during the 5th clock cycle, not the 4th clock cycle. So I can perform later on forwarding from the 4th clock cycle to the 5th clock cycle if I want to. But in general, here we need to have what? Here we need to have stalling. Forwarding alone will not work, and we need to introduce stalling before forwarding. And as I told you, because the issue here we have that the data is not yet ready, it is not yet retrieved during clock cycle 4. Okay, so I'm retrieving the data in clock cycle 4, and I'm trying to perform an execute operation at the same time for the add instruction. So the operands of the add instruction are invalid, because it will use what? It will use the values from the decode stage which are not updated. So yes, as I told you, forwarding, we directly forward to the execute stage and we bypass the decode stage. But in this case, I cannot forward because the data is not yet ready. So forwarding won't work because add needs the data in cycle 4, while the data is also retrieved in cycle 4 from the memory. So we have here a problem, and forwarding will not work. Therefore what? Therefore we need to stall. So how do we perform stalling, or what are the conditions that will trigger the stalling? We introduce a hazard detection unit in the decode stage. So like the forwarding unit we introduced in the execute stage, we will introduce a new component to the data path called the hazard detection unit, which will be present in the instruction decode stage, and it performs some conditions like the forwarding conditions. The first condition is I'm making sure that the id/ex.memRead control signal is true. So now I am trying to check that there is a load dependency between two consecutive instructions. So at the id/ex pipeline register, which is the pipeline register after the decode stage, I will have the load instruction values and its control signals. So the memory read control signal identifies or indicates that I want to read from what? From the data memory. So if the memory read is 1, meaning that I'm a load instruction, whether I'm a load word or a load byte or whatever, I'm a load instruction, and we have here an and if/id.register rs is equal id/ex.register rt. So now we are checking id/ex is the pipeline register containing the data of the load instruction, while if/id pipeline register is the pipeline register containing the data of the add instruction. So I'm making sure that the rs operand of the add instruction is equal to the destination of the load instruction. And as I told you, in the load instruction, it's an I-type instruction, so the destination of the load instruction will be register RT. Okay, that's why I'm comparing whether RS is equal RT or not. T1, which is RS of the addition instruction, is equal to T1, which is RT of the load instruction. If this condition is satisfied, this means that we need to what? We need to stall and take care. This tackles the conditions to stall. I'm not talking about forwarding. I'm talking when to insert hardware stalls. Okay, and hardware stalls are exactly like software stalls. It will insert a no operation, but it will insert it from the hardware level, not the programmer who will manually insert it in the software level. So yes, software stalls, the programmer checks the code and inserts no operations manually, as I will do when I test your project. But from a hardware level, there is a hardware implementation for stalls where the processor during runtime will insert the NOPs, not during compile time, during runtime. Okay, because during compile time it's considered still a software level, but during runtime I'm running already. This is what hardware level. So I'm checking the mem read is 1 and register RS of the add instruction is equal to register RT of the load instruction, and take care the mem read signal is from what? From the load instruction. Okay, so now let's move on to another condition as we had in the forwarding unit. We checked on register RS and we had to check on also the second operand, which is the register RT. So consider the following assembly code. The first instruction is the normal load instruction. I am loading some data from the data memory to register T1, but in the second instruction I am performing an addition instruction, and the second operand is the operand that is having the dependency. So as you can see, I am adding the value of register S1 to the value of register T1. Therefore, RT is now T1. RT is the second operand, and the read after write dependency is now occurring on RT and not on RS. Therefore, I need to check whether RT of instruction 2 is equal RT of instruction 1 or not. So we have the second pair of the condition. I am making sure that the id/ex.memRead, which is the id/ex, the pipeline register containing after the decode stage, which will contain our load instruction. The mem read control signal is 1, indicating that I'm going to read from the data memory, and I'm making sure that if/id.register RT, which is the second operand of the add instruction, is it equal to the id/ex.register RT, is it equal to the destination or to the target. Now in I format instructions, we do not say destination, we should say target. So the target register of the load instruction or not. Yes, it was T1 in the addition and T1 in the load. So this is the second half of the condition. So we have a pair of conditions to check on load hazards or load data hazards. I'm making sure that if I have two consecutive instructions, that if the first instruction is a load instruction, how can I know that the first instruction is a load instruction? That its mem read signal is 1. If the mem read signal is 1, meaning it's a load instruction that will read data from the data memory. And then I'm checking that the second instruction, the second consecutive instruction, the instruction that is following it, if one of its two operands, RT or RS, is equal to the target of the first instruction, which is RT, then we need to stall. These are the stalling, the hardware stalling conditions. So if we add both conditions together, we will separate them with what? With an OR. So I'm having id/ex.memread. We will always check on id/ex.memread, making sure that the memread control signal is 1. I am reading from the data memory, and I will have what? I will have this bracket opening and this bracket closer, and I will compare is rs equal RT, rs of if/id equal RT of id/ex, or the RT of if/id is equal to the RT of id/ex. So is the second instruction first operand equal to the target of the first instruction, or the second instruction second operand, the RT, is equal to the target of the first instruction. Therefore, I have an OR because one of these conditions or one of these equalities, rs equal RT or RT equal RT, will result in stalling, taking into consideration that we are a load instruction and the mem read signal is 1. Therefore, here it's an AND, but now I'm choosing whether I'm checking RS, the first operand, or RT, the second operand, is equal to the target of the load instruction. So we tackled how to detect that we need to stall. So actually, how is the stalling implemented or performed on the hardware? I mean, from a software perspective, we were inserting an OP instruction, okay? So now, how can I insert an instruction during runtime? I cannot. So I need to have a hardware implementation to simulate the no instruction or the no operation instruction. So there is a misconception that I want to clear from your minds. When I say id/ex, this means the instruction is starting the ex stage, the stage after the slash. Here, if/id, meaning that the instruction is going to enter the decode stage, okay? So the load instruction is going to be in the execute, and the add instruction is going to be in the decode, and the hazard detection unit will detect when the add instruction will be in the decode. Okay, so yes, I told you in a few moments ago that we'll assume the load instruction is in the decode and what? And the add instruction is in the fetch, because we fetch the instruction then adds its data at register if/id. We decode the instruction and put its data in id/ex pipeline register. But actually, the conditions will start to check after this clock cycle, after I put my data in the pipeline registers, which is the following clock cycle. Therefore, the add instruction will be in the decode and the load instruction will be in the execute. Okay? So even in the forwarding unit, when we checked for R-type data hazards, if we check the data pass implementation of the forwarding unit, we will find out that when I told you, or I talked about having 3 instructions, n plus 1 and n plus 2, instruction n will be at where will be starting the write back stage. So it will be after this pipeline register, and instruction n plus 1 will be in the memory stage, will be after this pipeline register, and instruction n plus 2 will be in the execute stage after this pipeline register. Okay, so when I have 3 instructions and I look for dependencies n plus 1 and n plus 2, n will be in the write back, n plus 1 will be in the memory, and n plus 2 will be in the execute, because n plus 2 is the instruction that is having a hazard, whether between instruction 2, n plus 1 and n plus 2, or between instruction 1, n and n plus 2. Okay, therefore the forwarding unit was present where in the execution stage of the instruction that needs to get the data forwarded. Okay, because the forwarding unit will provide this instruction with the correct inputs or operands to the ALU. That's why the forwarding unit is present in the instruction that has a hazard and needs the updated value. That's why this instruction will be n plus 2, which will be in the execute, n plus 1 will be in the memory, and n will be where? In the write back stage. That's why if I told you we have 3 instructions, the first one is n, the second one is n plus 1, and the third one is what? N plus 2. So if you want to check on the conditions, you can see that mem slash write back, meaning this instruction will start the write back, ex slash mem, meaning this instruction will start the memory, and finally id slash ex, meaning this instruction will start the execute, and therefore this is the instruction that has the problem. Therefore I'm checking for the register rs or the register rt of this instruction because it needs updated value. Therefore the forwarding unit is in the execute stage and this instruction needs to be in the execute stage with the correct values. Same goes to the hazard detection unit. The load instruction will be in the execute while the add instruction will be in the decode. So if we go to the diagram, we will find out that we introduced a hazard detection unit in the decode stage because the addition instruction, which is in the decode, needs to be stalled 1 clock cycle. I do not need to move this instruction to the execute stage. I only need the instruction which is in the execute, which is the load, to move to the memory stage, and I need to stall. I do not need to have anything operating on the execute stage at the next clock cycle. Okay, so instead of calling them the load instruction and the add instruction, I'm going to call them the n instruction and the n plus 1 instruction. The n instruction is the load instruction which is in the execute stage. The n plus 1 instruction is the add instruction which is in the decode stage. So what do I want to do? I want n instruction to move to the memory access stage so it can retrieve the data from the data memory, while I want n plus 1 instruction to remain in the decode stage. I want to stall the pipeline by 1 clock cycle. I do not want the n plus 1 instruction to move to the execute stage. So to perform this, to stop it or preventing from moving this instruction n plus 1 to the execute stage while maintaining that instruction n move to the memory stage, we need to perform stalls, which is performed using the hazard detection unit. The hazard detection unit takes as an input the RT of instruction n, which is present in id/ex pipeline register, which is this line. So id/ex.rt is entered to the hazard detection unit, which is the target or the destination of the load instruction, which is instruction n, and also it is taking the rs and the rt of instruction n plus 1 from the if/id pipeline register. So if/id.rs and if/id.rt are going as inputs to hazard detection unit. So I'm checking the rs of n plus 1 is equal the rt of n, and I'm checking the rt of n plus 1 is equal the rt of n or not. Okay. Also we have as an input the id/ex mem read control signal. So I'm checking that instruction n having the mem read signal is 1, meaning it will read data from the data memory, indicating it is a load instruction. So I have 4 inputs to the hazard detection unit. I have the instruction n rt, instruction n plus 1 rs and rt, and I'm having the mem read control signal of instruction n. Okay, instruction n data are stored in id/ex pipeline register, while instruction n plus 1 data are stored in if/id. Okay, now the hazard detection unit has 3 main outputs. The first output is called the PC write, the second output is called the if/id write, and there is a third output which acts as a selection to a newly introduced multiplexer. So let's go one by one. The PC write output is, now I'm in a hazard detection unit. I detected that there is a hazard and I need to stall. These outputs are the guidelines to stall, okay? They are the sequence to stall. They will perform the stalling. So, how can I perform the stalling? As I told you, I do not want this instruction in the decode, which is instruction n+1, which is the add instruction, to move to the execute stage. So how can I perform this? I need to keep this instruction in the decode stage. Therefore, I have two outputs from the hazard detection unit, PC write and if/id write. These will prevent the program counter and the if/id pipeline register from updating. And take care, these two outputs are control signals. They are considered as control signals that will prevent the program counter and if/id pipeline register from updating, meaning the PC write will prevent the PC from updating, and the if/id signal will prevent the if/id pipeline register from updating. Why? Because actually I want in the next clock cycle to also decode instruction n+1. Okay, I do not want to decode instruction n+2, which was fetched here. Therefore, whatever instruction I fetched here from the instruction memory, I do not want to update the if/id pipeline register. I want in the next clock cycle to retrieve the old instruction, which is n+1, which is the add instruction. And at the same time, I do not want to increment the program counter, because the instructions that I fetched, I discarded it. I did not save it in the if/id pipeline register. Therefore, I need to what? To fetch it again in the next clock cycle. So how can I fetch the instruction again? I need to prevent the program counter from updating. Okay, so we have two control signals that will prevent the program counter and the if/id pipeline register from updating. So in the next clock cycle, I will also decode instruction n+1 and I will also fetch instruction n+2. Okay, nothing new will happen. Now an important question arises. What are the values of PC write and if/id write? Actually, this is the trick. If PC write and if/id write are 1, this means update the program counter and update the if/id pipeline register. But if the PC write and if/id write values are 0, this means do not update the program counter and do not update the if/id pipeline register. Therefore, the signal name is write or contains the word write because it is indicating should I overwrite or should I update or not. So if it is 1, it means update. If it is 0, it means do not update. Therefore, the hazard detection unit, in case it wants to stall, it will output 0 in both signals. So if I want to stall, the PC write value will be 0 and the if/id write value will be 0. Otherwise, if I do not want to stall and I want to continue normal execution, the PC write and the if/id write will be 1. That's why they are called write control signals. Should I write or not? If I want to write, they will be 1. If I don't want to write, I will be 0. Do not want to write meaning I do not need to update. I do not want to update. But I want to write meaning normally update. Okay? Now, the last signal is we have, or the last output is a signal, and we have here a new multiplexer. This multiplexer selects between two values, okay? Or actually selects between two main values. Whether I'm going to take all the values of the control signals generated from the control unit, so instruction n+1 enters to the control unit its opcode and generates all control signals. This multiplexer selects whether I will take the values of the control signals, which is the first blue line, or I will force all control signals to be 0, and this is the second line. Okay, so this control signal or the third output of the hazard detection unit will select whether I want to have the normal control signal values or I want to force all control signals for this instruction to become 0. Now we need to listen carefully or take into consideration some aspects. What does it mean that I reset or clear all of my control signals? Making all of my control signals 0 means that no operation will be performed in any of the components in the data path. Okay, so I will not read to the data memory, I will not write to the data memory, I will not perform any register operation in the register file, and this indicates that what the instruction will not affect the pipeline. An instruction having all of its control signals 0 means it will not affect the pipeline because it will not overwrite any value, it will not read any value, it is just flowing in the data path without performing any logical operation. Okay, this is the exact definition of what? Of a no operation. So what will happen is I cannot physically leave a stage without having an instruction in it. Therefore, if I want to stall the decode stage which contains instruction n+1, which is the add, will actually move its data to the id/ex pipeline register. But guess what? It will move its data to this pipeline register, while if I want to stall, I will let all of its control signals equal 0. Okay, so this instruction n+1 will be moved to the execute stage having all of its control signals 0. I cleared all of its control signals, while I will remain with this instruction n+1. I will also decode it again, and instruction n+2 I will also fetch it again. So I will have at a certain clock cycle the memory stage will be having instruction n, which is the load instruction that will retrieve the data from the data memory. The execute stage will have a dummy instruction, which is instruction n+1. It will have instruction n+1 but with control signals 0, because this multiplexer, in case of stalling, will clear all the control signals. Therefore, the control signals stored in the id/ex pipeline register are all zeros. Therefore, this is a dummy instruction. Instruction n+1 now is dummy in the execute stage. It will perform nothing. Also, in the decode stage, I will have n+1 instruction. So I have two versions of n+1 instructions. Okay, a version in the execute stage and a version in the decode stage. But the version in the execute stage is dummy because it has its control signal equal 0, while the version in the decode stage will be the actual n+1 or add instruction. And here I'm going to fetch the n+2 instruction. So at a certain clock cycle, if I'm going to stall, n will be in the memory access, a dummy n+1 with control signals of 0 will be in the execute, the actual n+1, which is the add instruction with its correct control signals, will be in the decode, while n+2 will be in the fetch. So n+1, n+1, n+2 instead of what? n+1, n+2, n+3. So as you can see, the stalling occurred that I duplicated the n+1 instruction and I took a version to the execute stage because I cannot have an instruction not operating, or I cannot have a stage not operating on an instruction. I cannot have it an empty in the middle. So what shall I do? I am duplicating the n+1 instruction to the execute stage, but I am resetting, I am clearing its control signals. Having control signals equal 0, it will not perform any functionality. Okay, and then what? Since I prevented the if/id pipeline register from updating and the PC from updating, I'm going to fetch n+1 again in the decode stage. So I will have a new version of n+1, and I'm going to fetch instruction n+2 again. So when the load instruction or instruction n moves to the write back stage, I will have in the write back n, I will have in the memory stage the dummy n+1 with control signal 0. I will have in the in the execute stage the correct n+1 with the correct control signals. I will have n+2 in the decode stage and n+3 in the fetch stage, etc. So as you can see, this output or this control signal is very important because it will choose whether I'm going to pass to the next stage the actual control signals of the instruction, or I'm going to clear it so to prevent it from operating on any component. Okay, also with the PC write and the if/id write, whether I'm going to update the PC and if/id pipeline registers or not. So now we are done with the hazard detection unit and how to detect load data hazards, and actually how to stall our pipeline by 1 clock cycle when we detect load data hazards. Now I am done. If you have any question, don't hesitate to post it on Piazza and one of the course instructors will reply to you. See you soon and good luck in your final exam.